All right. So, yeah, this is kind of our first. No, it's not our first. I was gonna say it's our first section, our section on this module, but it's actually our third section. I think last week might have been a little, or the week before might have been a little sparse. But this is actually going to be talking about. This section is about calculus, review some calculus, and then really into gradient descent, which is the real reason why we're talking about calculus. So quickly, kind of going through like. I don't like to spend too much time on this because I'm not going to try to reteach you calculus, but of course it might be a good review. But just a quick, like, just with your fingers, right? Being like 5 being like, yeah, I remember calculus pretty well. And by calculus, I mean up to derivatives. You don't have to worry about like integrals or anything weird like that. But like, just show me like with your hand being like 1, being like, I don't remember anything about calculus, like completely. If you said derivative, I'd be like, derivative what? And then 5 being like, oh yeah, I can do calculus in my sleep basically for derivatives. Just a quick poll. So, okay, some 2s, some 4s, 3s. Okay, and Giovanna, I saw you came in 1 to 5 your calculus expertise. 1 being like, don't remember. Okay, and Thomas, I don't know if you can hear me. If how you feel with calculus. 5. Okay, cool. So, all right. So we have some good variety of people. And so if you've been really technical, calculus might be something. It's like, yeah, that's just another thing I have. For some people who might not have had like calculus as their background or like mathematics as a strong background, might be as familiar. So we'll do some quick review. But the good news for any people who are kind of like, ooh, like calculus, like maybe I haven't talked about that in a long time. The good news is that it's not super like important, in my opinion. It's not super important that you need to know like, oh, I need to know all the parts of calculus to do these algorithms. Really, it's meant to say, okay, like how you write these parts out. And we'll show this with how it relates to gradient descent in a second. All right. So I'm going to share my screen. And these notebooks that I'm going to show you today should be in the GitHub repo. It's possible that one of them is not. We'll see if we get to that one, or if we need to go into that one. Cool. All right. So basically there are 2 main ones, the derivatives, and I'll be honest, the derivatives one is pretty sparse, so don't feel like you probably don't need to reference it. I would probably recommend going into the material or the curriculum material itself. All right, so we're just gonna do a quick like review of what calculus, like, and really derivatives, what we're talking about. So a derivative is a rate of change. So does anyone like want to try to just verbally explain like what is a derivative? When I say a derivative in calculus, what are we talking about? Anything that comes to mind. I took a big one, didn't I? Rate of change. Okay, I'll give you guys this one since it's our first time back, right? So when I think of derivative, I just literally think like in my mind instantly, it's slope. Like basically it's just like how the line is changing, how this function is changing. Rate of change, I don't like using this rate of change thing, but because I like saying slope, because everyone from mathematics kind of knows what slope is. So in case you didn't though, I'm not trying to make you feel bad or anything, is that if you have like a function, let's say, for example, like a nice little parabola like this, okay, my funky parabola, and I put in like, say, okay, how steep is this part right here? Well, you can say, oh, it's kind of steep going, left to right, it's definitely like more downhill this way. We could write, for example, something called a tangent line, right? That would go straight off of here, right? And that tangent line basically is just touching that point that I care about. And of course, that tangent line actually has a slope, a rise over run. Well, it turns out that slope of the tangent line is the derivative. Like that's literally all it is, which makes it super convenient. Like I like to draw it in two-dimensional and stuff like that. I feel like sometimes derivative sounds very like intimidating, and like especially if you can't remember a lot of calculus, you're like, what was that again? Like there was some math and some D's and some other weird, little apostrophe stuff. Mostly it's like, oh, it's just slope. What's nice too is that and I'm not a good drawer, so I'm not even gonna try, but if you have a 3-dimensional object too, like a 3-dimensional function, if you draw a tangent plane, basically a piece of paper that's just touching one point on that function, that also that slope of that tangent plane would be the derivative. Now, in that case, the derivative would actually have, because it's 2 dimensions, x and y. But the point is basically, it's saying how steep that point is. And that's really all a derivative actually is. Second derivative is basically how steep is the steepness, basically how quickly is the steepness changing. You could go third, fourth, fifth derivative, right? Basically how steep this function is. That's essentially all derivatives are. So I just want to put that in your mind, being like, all it is about like the slope. And I think that's something that's relatively familiar versus like, I don't know, rate of change always seems in my mind like, I never talk like this, rate of change. It just seems weird. Okay. So anyway, that's kind of what overall derivative is. So a rate of change for a linear function. So before I kind of open this up, does the slope of a line change? I see some head shakes. No, right? So a linear function is a constant slope, right? And hopefully you remember this back from the famous equation that here in the US we always talk about, y equals mx plus b, right? Yeah, that good old function that we always had. And in this case, we always say like m is the slope. Well, if this describes a whole line, m is constant. So basically the derivative of this with respect to x will just be m, basically how steep it is. Doesn't change, okay? So that's what we say, basically a line or a linear function has a consistent rate of change or a consistent slope, right? So it's constantly going downhill, or it's constantly going uphill, or it's constantly staying exactly zero. Does anyone remember what the slope is of a vertical line, like a straight up vertical line? Kind of trick question.
Undefined.
Undefined, yeah. So another way you can almost think about it is like infinite. Although, you know, mathematicians will like start cringing if they ever say like infinite for undefined. Really, it means like it's really not defined. But if you think about it, if you have a line like this, that's a slope of zero. Its steepness is zero. Its derivative is zero. And then as it increase it up and up and up, well, depending how you're looking at it, if I'm looking at it like this, it looks like a negative slope. If you're looking the other way, you might see a positive slope. But as I move it up and up and up and up, basically the slope gets bigger and bigger and bigger, you know, more negative, right? So basically the absolute value gets bigger and bigger until basically I reach the biggest as possible, which is basically, in my mind, infinite, but undefined, okay? And you can kind of see this, and the reason why we say it's undefined, it comes from this guy. This is how we calculate slope. Basically, your rise over run. So going back to like, I don't even know when it was first introduced, probably in school, but rise over run, meaning how much you change in the y direction and how much you change in the x direction. And you can write this as y2 minus y1, x2 minus x1. But I like using those kind of things. I like to say, how much did it change in the y direction, up and down? How much did it change on the x direction? And saying that's overall. So the problem is that if you have a slope like this, well, the x doesn't change at all, right? There's no change in the x direction. So x2 minus x1 will just be zero. So that's why we say it's undefined, because anything divided by zero, we just call it undefined. Okay, so you can see this is basically how you would calculate the slope. Anyone, I think, probably in about at least 7th grade has learned at least something like this, you know, even if it's been a long time. Probably seen something similar to this. And this is really what a derivative is. Basically, you say, okay, well, instead of just doing the slope of just saying, and I'll draw a little picture here. If we have something, I'll draw a line. And I draw my rise, or I guess my rise over run. There's my delta y. There's my delta x, right? And that's my slope. Well, we can also do the same thing, like say, okay, imagine instead we had that as a tangent line. I'll try my best to make it tangent. Okay, and that's a point right here of the line. We would actually say, okay, well, that means that tangent line has that slope, and that's basically its instantaneous rate of change, if you ever heard that before. Basically, it's our instantaneous slope. And that's how we get our derivative, which is this guy right here. Basically, it's that we take a function, and this function right here, x plus delta x, you can just think of this as saying like y2. y2 minus y1, okay, is divided by delta x, which is just simply what this guy is right here. The difference is that we actually make that delta x, that change in x, as small as possible. So like on the function itself, instead of doing it like this, we'd actually would literally, in mathematics, I should say, take this function. I guess that's not the best. Should make it a little bigger. If we have our big old function like this, and I take, you know, this point here and this point here, well, this is separated by delta x. I guess I should use another color here. This guy right here, from here to here, that's going to be delta y, right? Or if I were to put this in the function, if this function is f, right? Well, this would be f of x. And this part right here would be f of x plus delta x. Basically, x plus some extra part. And essentially, that's just y1 and y2. So essentially that's what I'm doing right here in this guy. But the thing is, in derivative, we just make it as small as we can, smaller, 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 smaller for any function, and eventually reach these parts. Instead of having these 2 points, we will have 2 points like this, and then 2 points like this, and then basically until it gets really close, until it essentially is the same point. And that's what we have a derivative. And this is right here. Does anyone remember what this is called? Taking the, starts with the letter L.
The limit?
Limit, yeah, that's all the limit is. Basically, it's approaching as close as possible until that delta x is 0, essentially. Basically, until there's no difference between x1 and x2. Okay, cool. Sound good for everyone? Hopefully that kind of turned back the gears of, like, back in calculus, or, when you were first introduced to this kind of concept. So cool. All right. So again, going off of this guy, just rate of change of a nonlinear function. It's just a derivative, it's just that tangent line. So really that process of this guy right here, this is always going to be the same number on a linear function on a line because it's constant. But for a nonlinear function, that tangent line, the slopeness will change, right? On a parabola, you can imagine there's certain parts that are not very steep and there are parts that are very, very steep. And that's just a changing derivative, okay? So again, rate of change is just literally the derivative, okay? Any questions on this guy? Hopefully that feels pretty good, right? Cool. All right. So then it comes in some basic rules. And I was like, okay, that's what a derivative is. And we can, like, if we were in a calculus class, we would go into say, where we can do this, proving it to ourselves that yes, this is in fact true. And then we can say, okay, what are some general rules that we can do so we don't have to literally draw out the tangent line, take the limit, and do this every single time. You could technically, but we don't want to waste our time, right? So we have some basic rules of derivatives. So one is the power rule. Does anyone by chance remember what the power rule is? And it's okay if you don't quite remember.
Is it the one where you're taking the exponent and multiplying it by?
Yeah. So a good one is like, what if I have this function here and I take the derivative with respect to x? What would this be based on the power rule?
3 times x.
3 times x squared. Yeah.
Oh, yeah.
So yeah, so no problem. So basically you drop down 1 power. The general rule basically is you have x to the power of n, and that taking the derivative will basically say n times x n minus 1. Okay, so that one's pretty like turnkey. And this is nice because n doesn't even have to be an integer. N can be whatever number you want. I'll say any number you want. It can be a fraction, it can be pi, it can be whatever you want. So like, if you ever get some weird function like this, x to the power of pi, well, that's just going to be pi times, the derivative I should say, is pi times x times pi minus 1. There you go, there's your function. So see, derivatives, power rules are like amazing. Once we have a power or use the power rule, we're just like, yes, this makes life easy. So that's what you mostly see, which most functions are like this, okay? What is nice is that we can actually extend this a little bit further. So if we actually have multiple terms, so if we know the derivative, for example, of x to the power of 3 is 3x squared, okay? What would be the power for x cubed? So anyone got to guess what this derivative would be? I see Giovanna mouthing stuff. I can't hear it.
I forget I'm muted. A times squared. AX.
So x squared, and you said 8?
Oh no, wait. 3 times 4.
12?
Oh,
I think you had the idea. It's okay. It's getting late in the day. We're gonna go with that. But yeah, it's 12. Like Bardo kind of showed out. But basically, I think you got the idea, Giovanna. It's that 4 times this 3 part, and that gives us 12. Yeah. And so basically you're just like, oh, just basically the coefficients, you just ignore them essentially. There's ways you can prove this as well, but basically you can just keep them that way. Now we can actually add these parts together. So if we say, let's say we have, just quick review then, if we have 5x squared, what would be the derivative of this guy?
10x.
10x, good. And that's because we got 5 times 2, and then x, right? Cool. So hopefully this kind of brings up some memories and stuff like that, like hopefully good memories. But anyway, this should hopefully be like, okay, like pretty straightforward, right? So if I want to then take the derivative of, let's say 4x cubed, which we know the derivative of, plus 5x squared, and we take a derivative of this whole thing right here, okay, all we have to do is essentially say, what's the derivative of this plus whatever the derivative of this is. So in this case, 4x cubed we saw was 12x squared plus derivative of 5x squared, which is just plus 10x. Sorry, my writing's not that great. I blame it on the mouse, but I know my writing in general is just really bad. So, all right. So pretty straightforward. Like this is kind of like I'm like, if you can get to this point, you're like, sweet. Like this is what most functions are. You can start going to other parts like sine, cosine, the derivative of log and stuff like that. But the point is that you have some function, you can take a derivative of it and then basically produce this part, okay? So once we have that, we can actually do something like the chain rule. So does anyone recall what the chain rule is by chance? Just no one has to repeat it. I won't call you out or anything like that. But thumbs up if you're like, yes, I remember the chain rule. Sideways, like I remember hearing that with that. Thumbs down, like I don't remember it at all. Okay, good. So everyone's heard of it. Okay, Barto's got some thumbs down, but that's okay. All right. So the chain rule basically, I'm going to show you the really complicated part, and you're just like, oh my gosh, this is so complicated. I don't remember how this works. Don't worry, it's a lot simpler. I actually hate this way of showing it, but if you look at the chain rule, I guarantee you will see something along this. This is literally like what I copied off Wikipedia just to kind of show you the formalism. So basically the idea is that you have this function, h of x, right? Which remember, whatever we wrote is just like a function. We just say, put an x in there and you get something out, right? Some equation. So h of x, for example, could be something as simple as 5x cubed plus 2x squared, something like that. Okay, that could be h of x. Okay, and the point is there basically whatever number you put in for x, you just basically, to get h of 2, you just put 2 in for x and you get that number out. So we do this thing called like this little prime, this little apostrophe, that's just saying the derivative. So the derivative of h of x. And basically it's saying, well, if you can take h of x and decompose it, which is all technical words, decompose it into 2 separate functions, all you got to do then is basically take the derivative of the first function, take the derivative of the second function, and combine it in this certain way. So instead of having the function like this, which would actually be really easy, this would just be derivative off our product rule, or not product rule, our power rule, would be 15x squared plus 4x, right? You know, easy stuff, right? But if instead I had something where, let's say, get my drawing out there. If I had h of x is equal to something like, let's say 3 times x to the power of 4 plus 3x to the power of like 10, okay? Well, what you could do is you could technically, if you guys remember back in math, you could basically write this all out, figure out the full expansion, but that would be x to the power of 4 plus 3x times each other 10 times, which would just be a pain of actually trying to write that out. There's some tricks you could do, but it would be a huge pain in the butt, right? So, but what is nice though, you can say, wait a second, this h of x looks a lot like something else. If I said, let's say f of x here, or I'll put f of z just to make it like different. So f of z, if f of z is defined as 3 times z to the power of 10, well, that's a lot like saying, well, whatever this function is, put it in for z and we got the same thing, right? You're like, oh, okay, cool. So like basically I can make this other function within the function, right? Okay. And then you can say, let's say g of, I'm using different letters just to make it different, but it doesn't really matter what letter I use, right? I can say g of w is equal to w to the power of 4 plus 3w. Okay, and that's the inside part right here. Well, now what happens, I can say, well, that means h of x is really just saying f of g of x. So basically I have, you know, I put x in for this function right here, and it's gonna be x to the 4 plus 3x. And then I take that whole thing and plug it into this function for f, and I get 3 times that whole thing of g, which was x to the power of 4 plus 3x, to the power of 10, and that would be it. So what's nice is that if I know that's true, and that's what this represents right here, you'll see this representation sometimes, composition. It's basically written as like F circle G, which I always hate writing because it looks like fog, but like that would be like the function, right? But basically it's just saying, hey, this function is just representing F of G of whatever variable you put in there. That's what this is, okay? So if I know that's true, if I can write H of X into some function like this, well, then all I have to do is say, okay, what's the derivative of, let's see here, what's the derivative of F prime, and what's the derivative of G prime? So let's say we're just going using these letters Z and W. So what's the derivative of FZ right up there? Any volunteers?
30z to the 9.
Yeah, right, 30z to the power of 9. Okay, and then someone else wants to tell me the derivative of G, or I'll just use Z as well. Derivative of G.
4w cubed plus 3.
Perfect. And I'll keep W since that's what I had over there, but it doesn't matter what letter it is, right? Okay, so good. So I have those two parts. So like, all right, I have the derivative of F prime, or I have F prime and G prime. And then all I have to do is just say, all right, let me just write it this way. So what this is like, okay, this is a little complicated part, but it's not that bad. So F prime is whatever I put into it, Z in this case, whatever I put in, I'll put it in there. So G of X was just this guy right here. So I'm just gonna say, okay, that is W to the power of 4. I guess I'll use X, sorry guys. X to the power of 4 plus 3X. And then we're taking that whole thing and putting it in the derivative of F prime. So that means it's like, okay, that's just 30 of this guy to the power of 9. And then we just multiply it by G prime of X, which is just simply this guy right here. I'm sorry, I'm running out of room now. But 4X cubed plus 3, okay? And this is a lot easier for us to do. Like that took us a lot shorter time than us trying to expand the whole thing and then doing the power rule for each part. So that's where the chain rule comes in. And it basically means like if we can decompose our function into different parts, it makes it easy for us to calculate just the derivative of each part and then combine them in a set way. That's mostly what the chain rule is going through, okay? There's an alternative way of writing this as well. This is more classically done with non-Newton notation. I can't remember who wrote this first. But this basically, you'll sometimes see derivative, I don't know, if, just kind of like give me a nod if you've seen this written out like derivative of D. I can't write this very well. This should be a D, but D and then a fraction D of dx. Just give me a nod if you guys have seen that before. Okay, and basically that's the same thing, good. That's the same thing as just saying like F prime, okay? And then what it is that you just put in whatever variable or whatever function you want, and you just put that in there. So there's another way of writing derivatives, but it means the same thing as this guy. You'll see this classically done more in mathematics in a lot of papers and stuff like that, because you can start doing some interesting ways of structuring stuff like that, but it means exactly the same stuff as this, okay? All right, and the way you read this, just kind of quick reference, is this is the derivative of h with respect to x. And that's basically saying we're taking the derivative specifically of x. And then this one right here would be the derivative of f with respect to g. So this is kind of like, it looks a little mathy because they're like, oh, cool, I can just cancel these parts off. Right, I think this is actually wrong right here. Whatever, that's fine. But anyway, it's a derivative. Okay, so that is the chain rule. The good news is that for the most part, you don't really have to worry too much. It's not something that you're gonna have to do constantly over and over again, but it'll help us with the concept of actually finding the gradient descent. So going off of our basic rules, we now take the chain rule. Those are the two basic ones, basically power rule and chain rule. There's other rules and stuff that we can do, but those are the main ones that kind of go through. If you ever, I think there's something like the division rule, or I can't even remember what it's called. I never used that. Quotient rule. Okay, thank you. It's garbage. You don't need the quotient rule because the quotient rule is the chain rule, but it's just done with fractions. So it's like, yeah, anyway, these are the real powerhouses here. So the next part is like, if we actually find the minimum and maximum of derivatives, I'm not gonna go through the whole process of like, you know, you could like talk about, you find the second derivative of this part to say it's concave, concave up, concave down, and then you would take the first derivative to find the minimum, maximum, blah, 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 like a whole bunch of jargon. Basically, all you really have to know was saying we can find the min or max with a derivative. So the way we can do this is essentially say, well, let's say we have a function that looks like this. And remember, a function can be like whatever we want, right? So imagine you have something like this. Well, if I want to find the maximum, okay, the way we can do this is say, well, okay, we know the maximum is going to be the highest point. But what we really can say is like, well, a maximum is going to either go off to infinity, right? It's just going to keep going up. So like a maximum for like a line, it's just infinity, right? It's just going to happen at infinity. So we can kind of ignore that case. But if we have something where it's like, well, at some point it's kind of going up and down, doing some weird stuff and everything like that, there's a certain point where it's going to reach the highest point, right? And that highest point is going to be found when it goes up and up and up, and then it levels off and goes back down. And so it's nice that we actually can find this point right here. This guy right here is just when the derivative is 0, okay, because it's flat. So you can imagine at the very tip of that point, that's where the derivative is 0. So it's nice that we can actually find these basically different points, these critical points, we call them. And essentially there's like, okay, cool. Now there's a little caveat to this, because then you're like, wait a second. This is also a derivative of 0, derivative of 0, derivative of 0, derivative of 0. In this case, we would use the second derivative as well to basically make change. You can think of it as the rate of change of changes, but basically saying how are these things becoming steeper and steeper. And you can basically use that to test each point and actually figure out which is the most, which is the actual maximum or minimum. But the point is we can actually use the derivatives to figure this part out. And that's the key point, is that we can find our minimum maximum to begin with, as long as we know what this function is. And we can actually, we know from those points if we're going up or down off those points, okay? Does that make sense a little bit? I know this is very quick, and I didn't give you any details of like how exactly it is, but I think conceptually, hopefully that kind of makes sense. Like, yeah, we can kind of like figure out where those points of either max or min are. Sound cool? All right. So now we get to the fun stuff.